has done extensive work in the area of communication networks with focus on security of the networks. So I'll stop here and leave the floor to Professor Durresi.
Thank you very much for inviting me here, especially Professor Bertino. My name is Arjan Durresi. I'm with the Department of Computer and Information Science, Purdue School of Science at Indianapolis, IUPUI. Here's my information, my web page and my email address in case you might need some follow-up information. Today I will be talking about some security issues related to the next internet and especially over some heterogeneous environments. So here's the overview of the talk. I will spend a little bit of time to justify so-called the new internet and why we might need a new architecture for this internet and why the security will be probably the most important, the essential part of this architecture. Then I will describe shortly a proposal we are working, a new architecture, which includes security. And then in this spirit of security over heterogeneous environment, I will describe several of projects we are working. For example, security over continuity in sensor networks, security over heterogeneous environments where you have some nodes, mobile and some stationary, security over some networks of cell phones used in emergency situations, and combination of cell phones and sensor networks. So first of all, why we might need a new internet, and I will describe in more details what that word new might mean. So basically, the internet is somehow old. It's been 40 years ago they was invented and implemented, and there are several requirements which need more attention, and probably security is the first one. So basically, even though the research community has been working very hard to improve the security of the internet, still we are behind. For example, we are behind telephone network. Telephone network is much more secure than the internet, and as I said, we are trying hard, and probably now is the time to question the way we are trying. And other things which are, it's not only security, but many other aspects of the internet which might need improvement, like to make it more manageable, to make it more business-friendly, market-friendly. There are several non-technical aspects to be considered, as I said, economic and also social context. So this is kind of, in this point of time, a lot of researchers are working in this area. And actually, to capture this why a new internet, probably this figure will be kind of good example. So basically, the internet was designed, started with 4 nodes, kind of research experiment, and today we are talking about millions and probably in the near future about billions of nodes. And of course, I mean, it has been kind of almost a miracle that the same architecture has been working. When I say miracle, actually it's a lot of work, hard work by our research community these years. But still, one can think now that probably in this new reality where the dimensions are much bigger, we might need some new strategies, some new architecture. So as I said, this could be considered kind of very interesting time because not often people have the chance, community has the chance to challenge the architecture of the internet. So basically there is kind of consensus that new applications, new services might need more freedom, which the existing architecture might not be able to give it. There are new technologies going to the internet, like sensor networks, for example, which cannot have IP address, which have a lot of restrictions about energy and so on. Mobility has been a problem. We are aware that internet today is not very good about mobility. Security, as I said, we have continuous problems. And as I said, new services, new applications might need new things. Now, this is not just anymore just talk, thinking about the internet. In US, National Science Foundation is funding a lot of research in this area. We are talking about several hundred millions of funding already done and going on. Also other parts of the world like Europe, Japan are very aggressively funding and doing research in this area. So it's not anymore just talk, but it's also a walk. Now, why I say new here, quotation, is that even though we talk about the new internet, most likely the internet won't change overnight. Basically, won't be kind of revolution. So that 12 o'clock, you turn off the old internet, and 12:01 start the new one. Most likely this smooth transition, more than kind of new internet, will be kind of enhancement of the existing one. So this is at least my point of view. So in this slide, I will go very fast about things which, several features which we believe need to be improved, and I will focus mostly on security. So basically, energy, efficiency, most of devices today are supposed to be on. And in the future, most likely, the opposite will be true. An example of this new reality are our cell phones, which mostly sleep, and they work only when they are needed. Mobility is a big issue. So today, nodes mostly are stationary, and when they move, we have problems. And in the future, mostly, we will like our internet to follow us like a cell phone. Other things are the interface, human-computer interface will be more and more user-friendly, personal-friendly. End users won't be anymore just single computers, will be kind of distributed kind of array of small computers doing several things. Which leads us to protocol design. Most of the protocols today are symmetric. They don't distinguish big computers, small computers. In the future, we might have little devices talking to big servers, and of course, they cannot talk the same language, have to divide responsibilities. This leads to security. When internet was designed, nobody thought about security because there was no need for security. It was a research project, a few nodes, and now we are using the internet for anything: commerce, health, defense, and of course, the trust has to be built. It's not kind of given. The ownership, when it was designed, was a research project. Now it's business. It's provided by companies, by administrations. And some other more technical issues like sharing resources. For example, not always sharing is a good thing. Sometimes we might need isolation, depending on the case. For example, today internet is based only on packets, but packets are good for some things and secrets are good for other things. So in the future we might have both of them, packet and switching and wavelengths and other things to be switched. And the last, which is the most important, applications. Today we have email and web, and in the future, of course, we think we will have much more. And one glimpse of the future, for sure we have much more video. We see YouTube and we see other type of applications, which will need more services from the network. Now, with these things in mind, let us focus more on security. So basically, what we are doing in security, our way of fixing security is by putting patches. So we find a problem, we design a patch, we install the patch, and the next problem is there to be patched again. So basically, this cannot go forever. The other thing is that mostly our security is based on the node, so we try to build our castle to protect our node, okay? And this also is not a good idea, as I will explain. And our view about the security of the internet is that why don't we learn from the real life? In real life, we have security, right? Let us apply those lessons which our society, our civilization has developed in thousands of years. Let us apply these common sense rules on the internet. So this is the analogy of what we do today, the castle. And this has happened also in real life. I mean, people build castles, and unfortunately, always those castles were, sooner or later taken over by the adversary. So other things which could be problematic in today's internet is that authentication is done only at the destination. As I said, the castle model depends on the node, destination node. And all the resources in between are left to be used by attackers if they want. Okay, so basically this type of defense, we believe that it's very unscalable. And to show with a figure that this is what we are dealing with. So here is our network, our node, our computer, our castle, facing potentially the whole internet. So anybody could be our adversary here. And nobody is stopping them. So the only defense we have is here. So that's why I call it unscalable. Because here you are facing millions of potential problems. And of course, sooner or later this castle will fall. There is no way it can stand this type of attack. So, and the history of castles and buildings has long history. I'm mentioning just this Maginot Line, which was built by France and couldn't stand the attack from Germany. It was taken over in a couple of days, even though it was very very good from a security point of view. But again, it's not a question how strong the castle is. It's the model itself which cannot stand attacks. Another problem with security is that with this castle problem, so let us compare with real life. Because I said that let us take some lessons from real life. In real life, our houses are not castles. We don't have this kind of protection in our houses, right? Anybody can break them, okay? We don't have guns ready to fire anybody. And the reason because we have society, we have laws, okay? And bad guys are not stupid. They know that if they would do something, they will be, persecuted and most likely end up in jail. So that's the power of punishment. Now, why this doesn't happen in internet? Because in internet, most of the times you are not even able to follow and to understand who is the attacker and to persecute. Okay? So basically, we should like to build something which is close to real life and implements the same power of punishment or prevention of the punishment. Now, why architecture comes in the picture? Because, as I said, we are dealing with patches, and a lot of patches might be the signal that the problem is more fundamental. And to show you that just simple architectural decisions have big effects in security, let us consider just the IP address, or why the telephone networks are much more secure than the internet. One reason is that you cannot change your telephone number. Okay, it's assigned to you, and if you do bad things from your telephone number, your service provider would know, and anybody potentially could know and persecute you and make you accountable about that. On the internet, anybody can fake IP address. We get a lot of junk, and we can do nothing because if you follow, most of those IP addresses are fake. Because the IP address is soft. It was designed at the beginning to be soft, changeable, and you see this decision has opened the door of a lot of consequences. Okay, so basically that's the power of architecture. A small decision there has big consequences. So basically the same thing now could work in fixing problems. So we make better decisions at the architecture level, which can provide much stronger security. So the same thing with firewalls. Firewalls again are per hop behavior. So basically they guarantee just at that point what happens, but they don't guarantee anything about security end to end. What happens behind the firewall or before the firewall, nobody knows. So there are several alternatives. So one very extreme, which I mentioned here, this negative availability. Basically, in today's internet, the only thing you need to do just to access, and you could do anything you want. One another strategy could be that you can do nothing. basically, depending who you are, then you might get permission. But this is just to show you the extremes of different strategies. Now, with this in mind, with these lessons and with these needs, we have been working about new architecture, and I'm working with Professor Arjan here from Washington University in St. Louis. I'm helping him in this design. So I won't go in a lot of details of the architecture itself. Mostly I will talk about security of this architecture. So anyway, these are some features. The first thing we propose, and actually this is not really new, other people have proposed this, separation of addresses and IDs. So basically taking care of that problem of IP address, which is soft. So today addresses and ID are together. The only thing we have is IP address. We are saying let us separate them. We could leave IP address as an address, but the ID should be related to the person. Okay? In this way, when you go to the internet and you authenticate yourself, now your IP address is tied to your ID, real ID, and whatever happens, it's your responsibility, like in telephone network. Okay? Other things, in our architecture, we can have multi-layer of security, and I will describe that. It's part of the design. We include all type of communication, packets, circuits, wavelengths, anything could be part of the connectivity. IDs, as I said, will be separate from addresses, and we will have hierarchy of IDs. And this hierarchy of IDs will be related to the real organization. So this is actually the real novelty of our proposal, that the hierarchy of IDs fits with the hierarchy of real organizations. Okay? In our architecture, a lot of work is delegated to servers now, both to save energy, because we might have devices which don't have energy, and also to do a lot of things regarding security, like authentication and so on. Also, services might have IDs. Again, when you ask for service, you know the ID, and you don't care where the service is located. You just ask for the service which is closest to you. And another strong point is that we separate control from data plane. Again, this is not really novel in the sense that telephone network does this and enable telephone networks to have much stronger security. Okay? So basically, as I said, in our architecture, we try to get lessons from real life, and somehow we try to mirror real life. And this is shown in this slide here. So this is a process that's been going on for several decades, merging between telecommunication and networking and computing. And now, probably in the future, this will be the situation. There are all aspects of real life here, and they will be mirrored on the internet, so-called future internet, which will include anything related to connectivity. So let us talk a little bit about addresses, as I said, and names and IDs. So basically, name is human name, ID could be a number, and this could be an address. So we would like to separate them. Today, we have, as I said, in internet, we have this strange situation where we have just one address which is used as address and as ID. As I said, we would like to separate them, and actually addresses will be related to connectivity, and IDs and names will be related to other aspects like security, routing, okay, and everything else on the internet. Our architecture is built on objects. Object could be anything: computers, routers, networks, humans. As I said, we try to include everything now in this internet. Countries, departments, processes, and they might have hierarchy and could be recursive. So basically, a set of objects could be another object. These are some details of the architecture. Each object has its profile, including security features. And actually, this is an important point that routing is based on IDs and not addresses, which will be very good for mobility. Now, separation of data and control it's in architecture means it's kind of made more general. So we separate connectivity from management and control. For example, in the field, you might have different connectivity in the sense that you might have nodes from AT&T, from Sprint, for any type of connectivity in the field. And here might be the Purdue realm. So basically, even though nodes talk to each other at that connectivity level, the rules and the management is done here. So this enables a lot of flexibility. Today, we are under the tyranny of connectivity. Even security is done at the connectivity level. So we put rules at the routers, okay? And if you have to change anything, you have to go to each router and to change it. And depending on connectivity, you can do things or you cannot do things. Here, it's a lot of flexibility. It doesn't matter how the connectivity happens. At this level of management and control, you can apply your policies. Okay? And of course, these realms, which is management and control, somehow they fit very with organization. Let's say you have a university, has presidency, has different levels of offices, and the realm of networks will really mirror this situation. So you can put and place policies and rules at each of these levels, and they will apply to the below levels. So basically, boundaries between could be anything, could be technological, governmental, organizational, and so on. Now, let us focus more on security. What we talk so far has at least 3 strong features which are related to security. First of all, we have very well-defined context of networks. We separate management and control from data, and we allow the use of policy servers. So what does it mean, this well-defined bounded context? As I said, separating management from connectivity enable a given administration who has to handle that network to define policies at any type of level. For example, you can, like in real life, when you come to a country, you have to show the passport. That's the first level of security, right? At the country level. Then you go to building, you have another type of security. Inside the building, you can access some rooms and don't access others. So all these are rules defined by a given organization. The same thing could be done in network now. Depending on your architecture of the network and rules you want to apply, you can go rules for single nodes, group of nodes, level of nodes, and so on. So basically, as I said, this is just a mirror of real life. Separation of management, control, and data. Today, actually, one could send packets on the internet which could look like routing commands and disrupt the whole internet or major parts of it, because there is no separation between data and control. So the damage could be really big. So by separating them, we would like to make this not possible anymore. Policy servers. Now, in these realms, we can place servers, and these servers can help us to do all kind of authentication, which authentication is one of the weakest points in internet. And now, as I said, you can do authentication not only at the gates of your networks, you can do authentication at each level, at each node, whatever type of policy you might need to deploy. So basically, one output could be that you because of these policies could be designed in different levels, the security also could be like this. You have security at country level, at city level, at house, at room, whatever level you want. Basically, if you compare with the previous slide, the initial slide, which I said we are facing a very unscalable situation, here you don't wait for enemy here at your castle. You try to stop it whenever it's possible or whenever you want, okay? So, and this, it's made possible by these policy keepers, which are these servers in real areas, okay? So basically, organizations now are in full control of their security. So basically, we go from today, we the default situation is you permit anything. We try to stop as soon as possible bad things, right? So authentication, as I said, will be based not anymore on IP addresses, which means nothing. So what does it mean, IP address for this computer? Suppose now I launch some attacks from here, and who knows, it was me. Okay, you have to dig who was using this computer. But if my ID is connected with this computer for this time being, then I'm responsible. Okay, so it will guarantee non-repudiation of whatever actions. Basically, if you pick up a packet today, you are not sure who is the owner. There is an IP address, a source IP address, but what does it mean? It's faked or not? What we are proposing, each packet will have an owner. So you could see that whatever happens, there is somebody who did it. Okay. So and other many features which are part of the architecture. Now, how to go about this architecture? Because one criticism people have is that, as I said at the beginning, we weren't expecting that internet to happen overnight. So these are features, and not necessarily will happen at the same time. Most likely, people will take features from this architecture or other architectures which are being proposed, and in smart ways implement over the existing internet. For example, I can show you one case we are doing ourselves from our architecture. We have taken this mobility problem, and we are proposing to implement over the existing internet without changing anything. So how it works, it proposes a new type of service provider called mobile service provider, which will be kind of based on kind of value-added service. So basically, if you need mobility, you have to pay for that mobility, this special service provider, and this special service provider will follow you, will make sure that whenever you go, packets arrive to you and not at your home address, and this could work even today internet. Now, why this is not happening today? Because our mobility is based on mobile IP, and for some reason, not only technical but mostly commercial, service providers don't have incentive to apply it. Okay, but in this type of, let's say, light architecture of mobility, this service provider will be paid to do that, and of course, only people who might need security mobility will pay and will get this service. And the same thing can be applied for security and so on. So basically, I won't go in details, but just to show you that even in existing internet, without changing many things, we could have much better mobility. Now, let me move on some other scenarios. And the one we are talking now is regarding sensor networks. Now, a lot of work has been done on sensor networks. We are tackling another aspect. Sensor networks are built of small nodes, usually, with limited battery, and the life of this battery is not very large. I mean, sooner or later they will lose their energy, and we have to replace sensors. So basically, in real life, when you have a sensor network, you will have many deployments, not only one. Now, what happens about security? As I said, a lot of schemes are proposed about security, but when you have several deployments, then you might be in trouble because your adversary during time might capture single sensors, and when they capture a given device, they can take out all keys and all security schemes you have applied for the deployment. And now, if you keep the same keys for all deployments, of course, you will be in big trouble because they know now the keys. So what we are offering a way to better handle these many deployments from the security point of view. So instead of having the same keys for all deployments, we are saying keep each deployment with their own pool of keys. So at least if some keys are captured for a given deployment, they won't be able to use those in the next deployment. The problem now becomes how these deployments talk to each other, because to have the same network, they have to talk. So for this reason, we introduce some bridge nodes. The idea is a simple idea. In this case, in this figure, we show the application of this scheme with 2 deployments. So nodes number 1 are from deployment 1. They use a separate pool of keys, independent of the scheme. All type of schemes can be used. And nodes number 2 are of the second deployment, using another pool of keys. And as I said, they cannot talk directly to each other because they use different keys. And we use some bridge nodes, 1, 2 here in this figure, which one have keys from both deployments. And now, because these bridge nodes are much less than other nodes, we reduce a lot the probability of being captured, and also we reduce a lot the probability of compromising keys of other deployments. So there are some assumptions. So the enemy can randomly take all kind of nodes, take over. Now, so these bridge nodes could be normal nodes or could be stronger nodes in the sense that they might have more memory or more battery, and of course that will improve security. Here we have some analysis. I won't go in details. Actually, this is a published paper. You can get in my web page. The only thing to show you that here is the probability of keys being compromised between deployments. And as you see here in the formula, if the pool of keys has no keys in common, then the probability is smaller, much smaller than when you have the same pool of keys. So here are some experiments, some simulations, in which one we apply our scheme over different other schemes. So this part here is regarding random key deployment, predistribution, and this is Q composite random predistribution of keys, the other figure. And this is the kind of red one is the scheme itself, and here is when blue one when we apply our scheme, and this is the link percentage of links compromised. And you see now that the first deployment, the number of links compromised is the same. Of course, there is one deployment. Then you have 2 deployments. You see, it's almost half of the keys are compromised using our scheme. And third deployment more, the advantages keep building. As I said, the interesting part that you can apply this to this scheme to any other type of security symmetric security scheme. Here we talk about the overhead. Of course, this improvement in security cannot come for free. Basically, using intermediate nodes, the number of hops it's increased. And you see, this was, using the original scheme, when you apply our strategy, of course, we get more hops for each connection. That's the price to pay for security. Now here we analyze the role of bridges, these nodes, intermediate nodes, and the more bridges you have, better connectivity you can get. That's obvious. Now let me move to another scheme, and this scheme is when you have combination of fixed node and mobile nodes. Could be a situation like this. You have sensor nodes which gather information, and then you have some mobile nodes like cell phones which go and get this information. Again, how to build the security. And most of the proposed schemes, they use the same pool of keys for both stationary and mobile nodes. Again, we might have problems here because, for example, the enemy might be able to get some keys here. And because it's the same pool of keys, also they will get communication from mobile nodes, communication from other networks. So basically, security is compromised over the whole set of nodes or networks. So basically, to change this, to improve this situation, this is what we propose. We propose 2 schemes. In the first scheme, we create a separate pool of keys just for mobile nodes, and some of these keys also are given to stationary nodes. And of course, then each sensor network will have its own pool of keys to talk among each other. And in this way, we can improve a lot the security. So basically, when they capture keys from sensor networks, because sensor networks are much more vulnerable, the communication of mobile nodes won't be compromised, and the communication of other sensor networks won't be compromised. So actually, this increases security, and compared to the other technique, which I will talk in a minute, it has less overhead. The other technique is like this. It's called segmented key pool. Each sensor network has its own pool of keys, and the mobile node picks up some of the keys from each one of them. Okay. Again, we separate here keys between sensor networks, and that will improve security. The problem with this scheme is that it's not very scalable. Basically, if the number of sensor networks is huge, then you need a lot of pools. Okay. On the other hand, provides better connectivity, and this connectivity is paid by overhead, and also it's less secure compared to the previous scheme. Okay. Here are the metrics. We define the metrics: security, connectivity, and overhead. Security is probability of a link being captured by the enemy. Connectivity, probability of mobile nodes establishing secure links. Overhead, it's how much memory you need, basically how much keys you have to keep. And here are some results which compare schemes. So basically, here's links establishment versus overhead. And as you see that segmented key pool provides better connectivity and paid by more overhead. Security-wise, the segmented key pool it's less secure than separate key pool, the scheme in which one you have just one separate pool of keys for mobile nodes. And here's the relation between overhead and security. Again, this is the blue one, it's segmented key pool, and the other one is the separate key pool. And as I said, the separate key pool is more secure. And as I said, the segmented key pool is not very scalable, because as you see, if you have a lot of sensor networks and you have to have for each one a segment, the link establishment percentage goes down, so it's not very scalable compared to other ones. So basically, there are trade-offs between both schemes depending on the application you need. Now, another scheme which really I like in particular is this one, in which one we use cellular phones in emergency situation. So when something bad happens, like hurricane or terrorist attack or anything, most likely all communications are disrupted. All wires are cut, towers are down, and it's a really bad situation. Now, in this bad situation, and people die about this, and thousands of people have died in many cases. Even though we cannot talk, we have some devices, we have cell phones, which are very powerful devices, which can be used. The only way is that we have to change the way they communicate. Of course, they cannot talk anymore with towers, which are down, but we can make them talk to each other as ad hoc devices. They are very powerful devices. They can talk, cover a lot of distances. They have good batteries. So why don't we use this? So when everything is down, we start talking with our cell phones with each other. And we can use it for a lot of good information to go along. We can use them to talk to other areas of the network which the cellular phone could be working, or with the internet. So we are working in this area. We have designed the communication part of it, routing protocols and the rest. But also we are worried about security, because in this situation, yes, good people will use it for a good purpose, but might be bad people who might use this situation to create even more damages. Think about some terrorist attack. On top of whatever they might blow up, they may also spread the wrong information, sending people to wrong places. Okay? So basically security is very important. Now, one thing we try to achieve here, the first thing, we would like to achieve non-repudiation, so basically authentication. Now, we know that authentication in ad hoc network is not easy, because any node could claim that it's somebody else. Now, the feature we use here to increase our authentication is that these nodes before were centralized, were cell phone network. And then suddenly they moved in another mode. So why don't we use this mode, centralized mode, to distribute some keys for authentication, and then use those keys when they work as ad hoc nodes? So this is the whole idea here. We use identity-based cryptography. So basically, towers will distribute periodically keys, and then when they are out, they don't work anymore. Cell phones can use those keys, and those keys are guaranteed by the cellular network. Okay. So here are some details. So basically, we provide authentication. As we talk, we'll provide mobility management and trust management. So some details are here that basically each cell network or cell tower have its own private key generator, which will be used to generate keys. Okay, and also cell phones will have special IDs to be used in these cases, and all this information will be provided to them, as I said, periodically by towers. So here's what the tower, the base station, provides to a given cell phone: provides a special ID, provides the secure key of that cell phone, and also provide the public key of the tower or that network in order to be used to decrypt other people messages. And here's again, I'm going a little bit fast here. This also is published paper, and you can see the details. So here's, for example, how they communicate. Each sender now in ad hoc mode encrypts everything with its own private key and with its own ID, and then the receiver uses the public key of that area to decrypt the information and which was received, and everything is authenticated because this ID provided by the sender can work as has been given by the tower before. Now, of course, people also can move in this situation, so it's not you would like to talk not only on yourself area, but in other areas. Again, some details are here. Could be several solutions like having kind of umbrella just for mobility, or other type of solution like communicating between these areas when they were working at the cell network level. Now, yes, these are some analysis about overhead. I won't go in these details. One interesting problem which we are working to resolve, it's not being resolved fully yet, is that yes, we can guarantee the authentication, but some bad people, they might not even care if you are able to go after them. Terrorists, for example, they might even die to do something, so they don't care to tell who they are. So basically, we would like to build some scheme based on some trust management in order to detect malicious information in real time and stop that information. Now, this is a very difficult task because, first of all, how you distinguish bad malicious information. So that's based on your knowledge of the situation. So suppose I receive a message which says something, I should be able now to understand this is malicious or this is real information. Then after I realize that this is malicious information, for example, somebody telling me that, look, everybody should move from this area, that building is on flame. Actually, I see that building is not on flame at all. So it's clear now this is malicious information. I have to report to whom? Because these are ad hoc nodes now. So basically, this is a difficult problem because trust management is difficult in normal conditions, and these are very extreme conditions. Anyway, we are trying to develop some schemes here based on threshold cryptography. So basically, when something bad is reported, for each user will be a set of judges, let's say, and somehow they keep the trust score of this user. And when the trust score goes below a given threshold, that user will be blocked. Okay. Now this is not easy at all, because first of all you have to have these so-called judges, and they have to be trusted. And in order to improve our position, we are thinking to use some super judges in this type of scheme, which might be some police or other special figures which can be trusted more than normal users, okay? Or other type of users which can be trusted more than that, so we can improve the situation somehow. But still, building the trust here is not really very easy, and we are still working over the scheme. Anyway, there are some details about how this trust score is managed and what happens with them. I'm skipping those because I see the time is running. Now, another scheme I would like to discuss, the last one, is communication of mobile nodes, again, cell phones, and by now probably you see that I like a lot cell phones, and the reason I like them because probably this is the most successful wireless technology, and it's available, and we should make use of that. So here we apply that idea of realms and zones. So basically, cell phones and sensor networks, they talk to each other at the connectivity level, but we would like to apply rules at the management level. So basically, this might be fields of sensor networks. You go, for example, in a building, you would like to be guided, you go to subway, and whatever scenario. And now cell phones collect information. They provide this information to some gateways, because it's not that easy for cell phones to talk directly to sensors. So basically, we believe that some intermediate nodes, gateways, are needed to collect the information and then provide to cell phones. Now, the problem is security. So I go to a given sensor network, and how can I talk securely? How the keys should be distributed here. Again, we use this advantage of cell phones being centralized network. So basically, everything can go over this tower, these realms of towers, which can be considered more secure, more trusted than single nodes. And we use this feature to distribute keys. So basically, when a cell phone goes to sensor network, gets the ID of that sensor network, provides that ID to the realm of management realm, which is the tower level, and this tower level talks to the realm of sensors given sensor network, and in this way, now keys can come back here, the needed keys to talk to this gateway. And of course, you can do both asymmetric and symmetric encryption, depending on the availability of these nodes, how strong they are. But again, in both cases, the keys are distributed through the realms of towers of the cellular network, which can be considered much secure than a single node. Okay? So this is the major aspect. And then there are some details, again, based on, here we use again the identity-based cryptography based on the idea of the cell network and the cell phone itself. We distribute keys using this loop between the realm of sensor networks and the realm of towers. Here's the scheme. So basically, this is the cell phone. It provides the idea of cellular network. Then this is the cellular network provides to the cell phone the needed keys to be used to talk to the given gateway. So basically, this is the end of my talk. I would like to stress that security most likely needs some help from the architecture. It cannot be handled anymore just with pure patches. We have to think some more fundamental changes in architecture. And one example was the architecture I proposed. Then another thing is that security has to be improved a lot in these scenarios where heterogeneous environments are involved, different type of nodes. And we have to embrace this heterogeneity, like in cell phones, in our advantage. And using them these, for example, features of cell phones, we can really increase a lot of our security. So I think we are just in time. Thank you very much for your presence and for your attention. And I will be happy to answer questions.
Yeah, I was wondering, do you consider the possibility of some of these people who are working in these areas, usually it seems they put some exit door or backdoor channels so that they can come in and do something, and what are the chances of something that's happening over the whole thing all of a sudden?
Yeah, I mean, actually that's a very good question. This is a rule of thumb in security. If anything bad happens, look inside people. That's the first source of problems. And of course, for example, in our architecture, you can design policies which make accountable not only outside people, but inside people. So everything, I mean, you do somehow will be attached to your ID. So if you download 10,000 social security numbers, it's clear who did it and when it did it. Okay, so that's the key word, accountability, which we believe that this type of architecture has much more flexibility than previous ones. So this is one way to handle this inside problem. And of course, if people are aware that they are watched in the sense that whatever they do is attached to their name, they will be much more careful.
I have actually a more philosophical question, because I see it in the future, really machines being very autonomous and being able to do actions without any user telling them to do anything. Like they can really monitor events and activate things. Like a lot of, like IBM was working on these autonomic systems where they can self-manage the systems. So how would that work with your idea that we want to attach identity? So this can be solved, by which you will need to consider also machines or software as entities which must have an ID, not
so
only people.
For example, first of all, I don't think that's a good idea to leave everything on the hand of machines. But anyway, suppose that has been done by some mistake, then at least you will have accountability of that machine or that process. And as soon as something goes wrong, you know that this process went crazy or this machine went crazy.
So in any case, Professor Durresi is in UI PUI. So in case you are interested in getting papers or talking to him, you can get in touch with him. He once in a while comes to campus to visit the people in the CS department. If you are interested, let me know. I'll let you know when he comes next time.
Okay.
Okay, thanks.
Thank you very much.